All right, let's talk about Kubernetes. Today, we're diving into the system that has pretty much become the essential operating system for the cloud.
So, you did it. Your app is tucked safely inside a container. That's awesome. But now what? What happens when you don't just need one of them, but hundreds, or maybe even thousands, all needing to work together flawlessly? Well, that is the exact problem Kubernetes was born to solve.
All right, so let's dive right into that feeling of chaos. How do you possibly go from managing one simple container to conducting a whole coordinated fleet? Look, the jump in scale here is just massive, right? Managing one container is like being the captain of a little speedboat. It's manageable. But an entire fleet? Whoa, that needs a completely different playbook. It needs automation, it needs a serious master plan. And that master plan, that's what we call orchestration. It's basically the automation that handles all the heavy lifting. Deploying your containers, scaling them up when you get a flood of traffic, scaling them back down, and managing their whole life. So let's be super clear. Kubernetes isn't about building the containers, it's about managing them at a massive scale.
And this is the main analogy we're going to use today, and it's a really good one. I want you to think of Kubernetes as the port authority for your entire application fleet. Your containers, they're the cargo ships. Kubernetes is the one in the control tower, directing all the traffic, making sure every single ship gets exactly where it needs to go, smoothly and efficiently.
So, how does this whole port authority thing actually work? Well, it's fundamentally split into two main parts. You've got the brains, and you've got the muscle. And this right here, this is the key architectural split you got to understand. You have the control plane, that's the brains of the whole operation, it makes all the big decisions. And then you have the worker nodes. They're the muscle. They're the ones out there actually doing the hard work of running your applications. Okay, let's start with the brains. We're going to go inside the control plane. Think of this as the headquarters, the absolute nerve center for the entire cluster.
First up, the API server. This thing is the front door, the only door to the entire system. Every single command, every single request, it doesn't matter if it's from you or from another part of the system, it has to go through the API server. It's like the main radio tower and the security checkpoint all rolled into one, validating every single request before letting it in.
Okay, next we have etcd. This is the cluster's memory. If the API server is the radio tower, etcd is the official ship's logbook, the master manifest. It holds the one, single, official record of what the cluster is supposed to look like. And its number one job, above all else, is consistency. We need one source of truth, always. Then there's the scheduler. Its job sounds simple, but it is absolutely critical. When a new container needs a place to run, the scheduler is the one that finds the best worker node for it. It's like the master crane operator at the port, looking at all the available ships, checking their capacity, and picking the perfect spot for the new cargo.
And finally, in the control plane, we have the controller manager. Think of this as the fleet superintendent. It's constantly watching the cluster, and if a ship goes offline, the controller manager sees that reality no longer matches the plan and then immediately kicks into gear to fix it.
All right, so that's the headquarters. Now let's leave the command center and head down to the docks, to the ships themselves, the worker nodes. This is where the crew is doing all the heavy lifting.
On every single one of these worker nodes, you've got a kubelet. You can think of this as the ship's captain. It gets its orders directly from the API server back in headquarters, and it's responsible for everything that happens on its own ship. Starting the containers and reporting back on the node's health.
Working alongside the captain is the kube-proxy. This is the communications officer. This component handles all the complicated networking stuff. It manages all the network rules on the node to make sure that data traffic gets to the correct container no matter where it's coming from. And of course, every ship needs an engine room, right? That's the container runtime, something like containerd. This is the real low-level machinery that does the actual work of pulling down container images and firing up the application processes. It's the engine that brings the containers to life. So we've got the brains and we've got the muscle. But the thing that makes Kubernetes so powerful, the part that honestly feels like magic, is its incredible ability to heal itself.
And that magic all boils down to this one core idea. You, the user, give Kubernetes a desired state. Think of it like a blueprint for your perfect world. Kubernetes then spends all its time looking at the actual state, what's really happening right now, and it works tirelessly 24/7 to make reality match your blueprint.
It does this using something called a reconciliation loop. It's this simple but powerful cycle that just runs forever. First, it observes what's happening. Then, it analyzes the difference between that reality and your blueprint. And finally, it acts to close that gap. Observe, analyze, act, over and over again. Let's actually see how that works.
Okay, so let's say our blueprint, our desired state, says we need 3 copies of our application running at all times. And right now, everything's looking good. Reality matches the plan. We're happy.
But then, disaster strikes. You know it always does. One of the containers crashes. So now, the actual state, only 2 running replicas, doesn't match our desired state of 3 anymore. That reconciliation loop, it sees this difference instantly.
And boom, without anyone lifting a finger, without a 3 a.m. page, the controller manager acts. It tells the scheduler, hey, find me a new spot. And in just moments, a brand new replacement is launched. Reality is snapped back into alignment with the blueprint. That is self-healing.
This whole self-healing thing, it's not just a cool feature. It's a fundamental shift in how we think about and manage our infrastructure. We stop giving step-by-step commands and we start creating blueprints.
And this is the huge difference between what we call imperative and declarative systems. The old imperative way was all about the how. You'd give a list of specific steps. Create this, install that, start this service. The new declarative way is all about the what. You just hand the system the final blueprint and say, this is the outcome I want. You trust the system to figure out how to get there, and more importantly, how to stay there.
Okay, so let's tie this all together. Here's the final cheat sheet. Up in the control plane, our headquarters, you've got the API server, the radio tower. You've got etcd, the master manifest. The scheduler is the brilliant crane operator, and the controller manager is the watchful superintendent. Then, down on the worker nodes, you've got the crew. The kubelet is the ship's captain. Kube-proxy is the communications officer, and the container runtime is the powerful engine room making it all go.
All of these pieces work together in that constant loop, making sure your fleet always matches your blueprint. This creates an incredibly resilient, automated foundation. So the real question, the one I want to leave you with, isn't just about managing containers. It's, if your infrastructure can literally heal itself, what does that free you up to build next? What new possibilities does that open up? Thanks for watching.